Good morning, YouTube. So before I button this inverter charger up, I wanted to show you a little bit about how this thing works. So this is the TrippLite model APS1012SW. So the SW means it's a sine wave inverter. The 10 is 1000 watts, and then the 12 is that it runs off of a 12-volt battery. You can pretty much think of this as a UPS, or uninterruptible power supply. So it's built just like a UPS, except there's no battery inside of here. It's got an external battery connection, and then like a UPS over here, this line here is where you could plug this device into the wall, into the grid, and power this device off of the grid. And then the other cable over here is the output that you would plug your critical load into, the load that you want to keep running. And then the way this thing works is if there's power available from the grid, it will take power from the grid and it runs that over here, and there's two relays down here on the circuit board that switch power from the grid and back out to the load. So you're powering your device from the grid, and then if the grid power on this line were to fail, there's circuitry on this board that detects that, and then it'll switch these relays over and start pulling power from your batteries through the MOSFETs here. This is what's called an H bridge, and I'll talk about that in a bit. It runs that power through these two heavy cables here into this transformer, and that produces an AC waveform that comes back on this smaller red and black wire through the relays and then out to your critical load. And then if the grid power comes back on, the relays switch and go back into basically a bypass mode. It just brings power in, sends it right back out, and then it also charges the batteries. If the battery voltage had dropped while it was running on battery power, it'll use this same circuit here to pump current back into the batteries and charge them back up. This is a UPS basically, but you can add whatever size battery you want here, So that's why they call it an inverter, because it can take DC power, inverts it into AC power, and sends it out this wire. But it can also take AC power in, convert that to DC, and charge the batteries. So if you look at the whole unit, about half of it here is the transformer. So it's got this really big heavy transformer over here on the circuit board. You've got about half of the circuit board is devoted to these power MOSFETs in this H-bridge configuration. And then of the remaining board, you've got this corner down here is all of the AC switching. You've got the relays, you've got a filter, there's a bunch of MOVs and surge suppressor type circuitry, and there's also voltage monitoring to decide when the input voltage has gone low enough that it needs to switch over to inverter mode. And then the rest of the circuitry here from this section here is basically all of the inverter and charger logic. So this does all of the switching and controlling and generating waveforms and charging the battery and deciding what to do. And let's see, let's look here. I've printed out a couple of diagrams here to help you understand the way this works. These MOSFETs down here are in what's called an H bridge. So you can see it kind of looks like a letter H. You've got a vertical row of MOSFETs, another vertical row, and then the cross piece. This is shown as a motor, but in this case the load is a transformer. So you've got a transformer with a low voltage, approximately 10 volt winding here, and then the output of this transformer right here is a 120 volt output. Here's your H bridge. So here's the battery side. There's your battery connection, and there's 5 MOSFETs here, and there's 5 MOSFETs here in parallel, so you've got a total of 10 on that upper heat sink, and then there's the 2 lower heat sinks that are separated here. They're tied to ground or 0 volts here at the bottom, and then you've got your load connected here and here. So that's how that's set up. That's what's called an H-bridge. So the way you run that is these MOSFETs get turned on in diagonal pairs. So in one direction you have your battery voltage, you turn on Q1 and Q4, that lets current flow through the load that way. So you get one polarity, and then the other cycle you turn on Q3 and Q2, and now you're running current the other direction. If you just turn this on and off, you're just going to get a square wave, and you don't want a square wave, you want a sine wave. So the idea is you turn it on and off quickly, and I'll show you that here in a bit. And then back to this one, you run that output through a low voltage winding, and then you get your 120 volts out of the high voltage winding. So let's see if we can take a look at that here. And I've got it set on AC volts, and if we come down here, you can see it's right about 10 volts across that pair of MOSFETs. So you're pumping roughly a 10 volt AC voltage into these 2 windings, and then the red and the black wire here coming out of the transformer is 120 volts. Yeah, so there I'm on frequency there. I've got about 189 kilohertz. So I'm not sure if that is the primary switching frequency or if that's a higher order resonance, like a harmonic of the switching frequency. But the idea is you're generating a sine wave by turning the thing on and off. The higher the voltage on the sine wave, you're leaving this turned on more, and then when you get down close to 0, you leave it turned off. So they're probably doing some sort of pulse width modulation, switching it on and off in a sequence that produces essentially a sine wave. Yeah, we'll try the small meter here. I don't know if you can quite see that, but it's showing about 22 amps. So you've got about 22 amps flowing in those wires there at 10 volts. And then out here, you've probably got about 2 amps at 120 volts. So the idea is they're switching these high current, low voltage leads, switching those back and forth. They're using the transformer and the inductance in there to filter out all the high frequency components so that out of the output you get a nice 60 hertz sine wave. But anyway, that's the way this thing works. It's basically a UPS, so it'll run just like a regular UPS. If I were to plug this cable into the wall right now, it would turn off this part of the inverter. It would no longer be generating a sine wave, and instead it switches these MOSFETs into a battery charger mode, and it pumps power backwards into the batteries. But yeah, I think I'm gonna button this thing back up, put the case back on. I'll get my cooling fan controller mounted on the top. That's my temperature sensor. So I just have a magnet there with the temperature probe glued onto it. So that just sticks onto the steel of the power transformer there. And this is very common design. A lot of companies use the same sort of design. So it's a pretty versatile little device here. That was one of the reasons I bought this about 5 years ago, was it had a lot of functions built in. So far, other than the fan failing and causing those capacitors to blow out, I've not had a single problem with this unit, and I've pushed it to all of the limits. It'll do 1,000 watts of output, In fact, it'll go up, I think it does 1500 watts for 30 seconds, and it does surge output 200 amps of DC input, and it'll do 2000 watt output for, I think, a second or a half a second. Every specification I've tested, this thing meets. It'll actually do everything they say it does. But anyway, I just wanted to show you how this works inside. So if you have any questions or feedback on that, post up in the comments section below. And otherwise, thanks for watching.